Well, good morning, everybody. Hope you're having a great weekend. No sickness, no nothing like that. We don't want that going around. Today I want to talk to you a little about a book that I've been reading. I have been part of Simon Dan's book club, and the book we're reading right now is Forces of Nature by Brian Cox. I'll put the information in the description. This is a really good book. I recommend it highly. And in fact, I want to recommend Dan's book club. He has picked several books that are so far very interesting, very easy to read, easy to understand, and they're pretty low cost. I think this one was like $12. And so if you haven't already, you might go look over at his channel and check out his book club. I'll put a link to that too. But I wanted to talk to you a little bit about, of course, gravity, and the way he talks about it in his book. And hopefully you'll get some insight into this that you don't hear always. So, seen from space, the Earth, the planets, all look like spheres. You look at the Earth, the larger moons, all the planets, the sun, they all have this spherical shape. You begin to look out into the galaxy and into the universe, and you see that all stars have this spherical shape, and the exoplanets that they've looked at all have this spherical shape. And seems quite a common occurrence, and maybe a curiosity to those of us that are, of course, bound to the Earth. But there's a reason for this. There's a reason why all these things are spherical, and there's a we need to think about what is it that could affect the shape of a planet, a moon, or a star. It can't have anything to do with their composition. I mean, you look at Jupiter, Saturn, Neptune, and Uranus. They're very different than Mars and the Earth, Venus and Neptune. You look at the moons. The moons are a very different composition than the planet they circle. It can't be the composition. It can't be the amount of water, because Earth is obviously the planet with the most water. It's possible some of the moons have water, but it's different forms, and so we have to wonder. And then we have the stars like our sun that are some kind of a nuclear furnace, but completely different than each other, and yet they all have this one thing in common, that they're all a spherical shape. And so we have to wonder about that. The first theory of gravity that was written down and published was by Isaac Newton. Surprise, surprise, we've all heard of that. It was 1687 in his Principia, and he published a lot of things in there, but gravity was one of those things. Just so I can make sure you know, the apple never fell on Isaac Newton's head. So all these, I guess we'll say flat earthers that tell you, gravity just, an apple that fell on his head. Well, it wasn't. It was postulated and discussed among scientists for many years before Isaac Newton, but he was the first one to actually write something down and have it published. And his work was inspired by the work of Johannes Kepler. And so he wrote down all this, all this work is carried over. It's all builds upon each other. That's one of the things that some people don't understand, is that in science, all the work is built upon the work of others. And, if you don't have some kind of foundation, then all of this work is just garbage. And so, we have this Newtonian gravity, and we've seen how that works on the Earth. Things that fall, things that move under gravity. It's not just things that fall. So when you hear it talked about relative density, you can argue that over things that fall, something that falls out of an airplane or something, but that doesn't explain all the other things that you have to have gravity for. And you can't just say, it's we fall down to the Earth because it's our natural spot where we are held down. That's not a scientific principle. And so Newton's gravity also had to do with the orbits of the planets. Newton studied the orbits of the planets and how they work, so that he came up with his equations. But in 1915, I'm sure you also all know by now that Albert Einstein came up with this precise description of gravity. Newton's theory doesn't have anything to say about the mechanism about which gravity acts between objects, but it does allow us to calculate the gravitational force between any two objects anywhere in the universe. Einstein's more accurate theory of general relativity explains why we had spheres. But to answer this question about spherical planets and whatever, we don't need Einstein's elegant but significantly more mathematically challenging theory of general relativity. And trust me, it's, a very challenging calculation. It's off. Brian Cox says it's like using a sledgehammer to crack a nut. You're using way overkill to use Einstein's theory of relativity for that purpose. So we can go back to Newton's simpler theories. So general relativity would give us the same answer. Those two things work in common. You can't say we throw out Newton because we've got relativity now. That's not the way it works. And we won't. For this purpose, we want to look back at Newton's law of universal gravitation. And you see the formula there on the screen. F, which is the force, is equal to this big G gravitational constant. The product of the two masses divided by their radius squared. So the way I like to think about it is Newton postulated that the force was proportional to the two masses. So he multiplied the two masses. That gives you sort of a kilograms squared on the numerator. He also knew that the force was inversely proportional to the radius. The further away you get, the weaker the gravitational force becomes. So you divide, because that's inversely proportional. You divide by r squared. I think of the square in the denominator because of the two masses in the numerator. So you have a square divided by a square. Then you have to have the constant, because the constant is like a gauge to find the relative distances of these, or the relative sizes. So you have the constant. Now then, you've come up with an equation. We want to mathematically try to use the equation and see if it works. Lo and behold, they do have this relationship. They have a value for G that doesn't change. That's one thing you for sure don't want, is your constant to be different every time you use the equation. So he looked for this simple equation to talk about the way that planets move around the sun. Then Kepler, his empirical laws of planetary motion can be derived from Newton's laws of gravitation and his laws of motion. He has remember the three laws of motion. So this is why you might say Newton's equation is elegant, because the Newtonian gravity builds into Kepler's laws. They support each other. The observations of planets, of the movements and so forth that these guys did, supported their calculations. So the math doesn't stand by itself. The math is not some kind of magic. And they had to have the observations to do all these calculations. It amazes me because they did just hundreds and hundreds and hundreds of these calculations with these huge exponential notation, and they did it all by hand. So we have, for example, the planet Neptune was not known, at this time, and by all these calculations they did by hand, they discovered that there was a little bit of difference in their observations to the math, and they discovered, or they postulated there must be another large planet out beyond Uranus. And so they did some calculations. Again, this is all done by hand, and they figured out about how big Neptune should be, and where it would be in the sky if it was a planet rotating around the sun. And so they trained their telescopes on that area, and lo and behold, there was Neptune right there where they thought it would be. The amazing thing is that the math predicted where the observation would take place. The math and the observations go hand in hand. Again, you can't throw out the math, you can't throw out the observation. You have to have both of those things. And so another thing I wanted to talk about, and I watched this in the book. He talks about Mars, planet Mars, which is all in the news lately. And if you look on YouTube, it's all over YouTube right now. So Mars, compared to Earth, is a much, much smaller planet. It's 6.39 times 10 to the 23rd kilograms. So it's much smaller than the Earth. You have around 10% of the Earth's mass. It has a radius of about half that of Earth. And if you do a quick calculation, you find that it has about 40% of the gravitation. So you weigh about 40% of what you would weigh on Earth's surface. It has about 10% of the atmosphere of the Earth. So it's got a very, very thin atmosphere, and it's got very low gravity. So it's all in the news lately because of Perseverance, which has now landed on the moon, and this Integrity helicopter that NASA has designed. Of course, everyone, they talk about NASA or Mars has no gravity, or no atmosphere, I'm sorry. Mars has no atmosphere, so there's no way that helicopter could fly. And they've just got this, they've got everything turned around backwards. It's funny that they don't believe that there are planets or stars or space, but they can also talk about the helicopter on Mars. So And we talk about gravity, and that gravity was what brought the planets to the spherical shape, and there's a symmetry to it. It takes this symmetry that pulls all the matter together into a sphere each time, and gravity has to do with the mountains, the water that holds its place in the oceans, and that this gravitational pull is strong enough to overcome the oceans. It will overcome the largest mountains, the largest rocks, whatever, and yet it will let the smallest butterfly be able to fly. And I think that's the clincher of this gravitational attraction, this gravitational force that affects everything in the universe, everything particularly in our solar system. And I think it's important for us to remember that it is a force. It acts as a force because it is a force, and if you think of it that way, you'll be a lot better off. So that's really all I had today. I hope that you have a good week, and we'll be looking at some new things next week. Please come back. Do like and subscribe if you can. I would appreciate it. Tell your friends and get them to come watch. I could use some extra views. So with that being said, let's have a good week, and we'll see you next week.